Good morning, everybody. How we doing? Thank you, Omar.
Good morning, Dr. Terrell.
Elvin, how's it going, buddy?
Going good, sir.
So, have you ever heard of Alvin and the Chipmunks?
Yeah, I've grown up watching that thing.
Got it. Okay, I'm not going to say anything else. Nothing more. Oh my gosh! Oh my gosh! So, it started already. I'm having political conversations over Facebook, and it's a good thing. It's a good thing. Opening my mind a little bit. But anyway, it's a good thing. It's opening my mind in the sense that I am beginning to contemplate the views of others. You know, that may count as ever so slightly open in the world of minds.
Oh. Whatever makes you happy.
Oh, God. Well, you know, there's this thing called well, I'll just use it from my perspective. It's called your inner Trump, right? And probably there are people who would say maybe your inner Biden or whatever. Maybe they wouldn't say it, but I think that there's something to be said for embracing all parts of yourself. You know? Just like, okay, so this is part of me. You know, I'm at war with it right now, but anyway. So let us see here. Are there any questions about uncertainty propagation that I have not addressed? Does anybody want to lodge a complaint? Throw a flaming pitchfork over the internet? Anything like that? No? See, now that surprises me.
No, it's just something I have to practice.
Yeah. Okay, that's true. That's true. Basically, you know, we're very familiar with with equations, solving equations, but carrying uncertainty through equations is a little bit different skill. And the skills that we're supposed to have now are they're like 6 rules or so. There's multiplication, division, addition, subtraction, exponentiation, and then logs, natural logs, 10 to the x and e to the x. And those are, I mean, there's a simple calculus definition behind all this, but I'm just sort of going with the textbook now where we're not going to touch that. But these rules are, they're important, right? So in any case, practice them, they'll come up again, but they probably aren't going to make the difference between passing and failing, you know. But they will make a big difference in your grade. So, don't say that, Roger. Okay. So now we're going to talk about statistics, and I'm going to try to keep this fairly short. Well, we do have basically 2 periods. We've got this week plus part of next Tuesday to talk about it. So, yeah. So statistics, we'll talk a little bit about the Gaussian distribution. Everyone's favorite distribution. You know, basically, it's pretty shocking how often it applies, but it's also equally shocking where it's used. It has no business being used, you know. Oh, goodness. Okay, and then for some strange reason, we're going to compare standard deviations first, right? And it's a real strange thing for me, but let's do it. Normally, I start with confidence intervals and t-tests, and then I go on to like F, if I even touch it. But we're going to do F-test right away. Okay. And then confidence intervals, which is how to say something meaningful with statistics. Like if you know, like, let me say something not completely bizarre. You can, once you've done your stats, you get a population of data for which you believe to have a Gaussian distribution underpinning it, you know, that basically make it up. Then you can say that, okay, so long as this data comes from a Gaussian distribution, I can be 95% confident that the mean lies within this interval. Basically, that's what you can say. That's an important thing, right? Because like you can specify the amount of time that you might be wrong and the amount of time that you might be right about making a conjecture based on data, right? And the assumption that it's Gaussian, of course, right? Then you can compare numbers with a t-test. And say these means agree or disagree. Again, with this idea of a 95% confidence. And then you can do it all with a spreadsheet. You can test with small collections of data. You can test for an outlier. And this is sort of like a 95% no confidence test. You know? Then we'll talk about least squares. So, as an example, you can think of a blood glucometer. And this is cool because this is actually how they're built nowadays, right? They give you a little stabby thing, and it pokes your finger, draws a little bit of blood, and it's actually not painful. I tried one out the other day. And then you just put the drop of blood right up against the edge of this little, it's like a little Kapton strip with a little piece of glass on it, like a super thin piece of glass. And you get the blood to touch the end of that, and then it wicks up, it sucks up in there. And there's 3 electrodes in there. So it makes a 3-electrode electrochemical cell. And then in the working electrode, there's glucose oxidase, and that turns glucose into peroxide. And you oxidize the, or reduce, probably reduce the, I don't know, oxidize or reduce the peroxide. And then the rate at which that happens gives you a reading that it can be related back to the glucose concentration. So now one thing about these is that if you give them identical specimens or identical samples, they will fluctuate, you know. you know. And so, for example, if you took a glucometer and you read a 99 milligram per deciliter standard, and you read it 5 times, you might get 91.4 as your average reading, right? You can say, well, is my blood glucose reading correct? Well, no, it's not correct. It's very unlikely to be correct, right? Given this distribution of results, right? And you have to ask yourself, well, that means that I have to compensate for this if I assess health issues. I may be using it wrong, or the meter could be malfunctioning. So there's a lot of questions that come up about this, and we will touch on all of these eventually. So anyway, let me just move on. I sometimes hate saying, "Oh, and we're going to touch on this," and we never do. So maybe we'll touch on this. So. So the stats that we're going to learn give us the ability to accept conclusions or reject conclusions, right? So, and you know, it's just based on the probability that they are correct or incorrect, right? So, first of all, let's look at the distribution from whence they come, right? And so a distribution is a set of data that tend to cluster around an average value, right? This means that they have a central tendency. And a central tendency means that more of the data will fall near the average than further away. As a matter of fact, the rate at which they fall away on either side of this distribution is given by the negative exponential of the difference squared. And so that makes it actually symmetric around an average value, right? So interestingly, that immediately places sort of some puzzling limits on the applicability of the Gaussian distribution. Because, for example, in many cases, it would not be physical to say that you got a negative answer. It could be a concentration or something. And a negative concentration might be non-physical. It could be the radius of a pore. And a negative radius is non-physical. And a negative number of heads when the coins are tossed is physical. So you have to be careful when you're getting close to zero. If you're further from zero, a coin toss, or a toss of a collection of coins, I should say, will obey this negative exponential squared thingamajiggy, which is called a Gaussian distribution. So, so this is if an experiment is repeated 400 times, and it's 400 times with 50 coins, so it's a ton of individual coin tosses here, right? And this is when it's repeated 20 times, you know. You can see that it's already getting kind of sparse, you know. And if you use just 3 or 4 data points here, which is much more typical in chemistry, then not only do you not know if they're what the average is with great confidence, you don't know the standard deviation with much confidence, and much less do you know with great confidence based on a limited set of experiments if the resulting pattern should be Gaussian. So, with those huge qualifiers ahead of me, I'm going to plow forward, right? So we're going to assume Gaussian distributions for everything. Oh, and we're going to, then we're gonna work with limited data sets, basically. Okay. So you've all seen these formulas for a population, which is a group of values of X, right? So, it could be, the height of students, or it could be, whatever. It could be anything, right? And everybody has a value, right? And you can take an average by adding them up and dividing by the number of students, right? And that will give you X bar, right? Now, one thing that we don't often think about in this case is that X bar here implies that the data come from a Gaussian distribution, right? Or at least a distribution with a central tendency, right? With a tendency to converge on one value. Right? So that is one interesting sort of caveat there, right? But again, we're assuming Gaussian, so we can move forward, right? And then the standard deviation here is given by the sum of the squared differences between the individual points in the population and the population average. So the sum of those squared deviations divided by n minus 1, n is the number of data points, right? And then you take the square root of the whole thing, and that gives you the standard deviation. The standard deviation is equal to the width of the distribution that results. It's the area within which 65% of the results will lie if you repeat the experiment a bunch of times. So, so if you have X bar plus S and X bar minus S, that forms an interval around X bar within which you expect about 65% of the data to fall. So, and we're going to talk about that ad nauseum, of course. And then one thing that we should note here is that as the number of points in the data set increases, then the average approaches what's called the population mean, and the standard deviation approaches its ideal value, whatever that is. It's the population standard deviation. And sometimes there's two formulas for S, one that's divided by n and one that's divided by n minus 1. And the population S is divided by n, and the sample S is divided by n minus 1. We'll normally use a sample S, but for larger samples, it doesn't make much difference. Right? The difference between dividing by 20 and 21 is not large. So in any case, you're starting to get the idea here that we're not looking for exact values when we're calculating S. So now, standard deviation is a metric of reproducibility, right? So reproducibility here is one thing that we can assess from repeating an experiment a few times, right? Accuracy, you need standards. So here to do accuracy, you must have standards to do this. But everything we're talking about right now is all about precision and actually not so much about accuracy. And whenever we get a result, right, one way to express the mean and standard deviation of the result is X bar plus or minus S and then parenthesis n equals whatever. So like if you have, 37% chloride plus or minus 1%, and you have 3 replicates of the experiment, you know, 37 plus or minus 1 and equals 3. Oh yeah, and also the average, the standard deviation should end in the same decimal place. So let's show. Oh, wait. No. There we go. The camera view. Okay. So, what that means is that if you say you did an experiment to measure percent chloride, right, then you got 37.52 plus or minus 0.12% for n equals 4 determination, right? This is really all the information that's needed to characterize this result. Right? That's the first thing to say about it. The next thing here is that 37.52 plus or minus 0.12. This is the proper way to do this. So, and the reason here is that these decimals are assumed not to be significant, or basically they're unknown. Right? So we don't write them because we don't know them, even though a calculator will spit them out. We actually don't know. So this is S here, in this case, is written with 2 sig figs. SF. Significant. So, and because in this case, S is close to 1, we really do need 2 figures as best. Right. And actually, 2 sig figs can pretty much always work in the in the uncertainty digit there, because so but 1 sig fig is only if it's like maybe 5 or greater, and 3 sig figs is basically only if n is greater than like 20 or something like that. That makes sense. So what I'm doing now is I'm making a connection between significant figures and standard deviation, right? And really, standard deviation is the mother of the significant figure. Well, the statistics is the mother of standard deviation, right? And the more we know about the standard deviation, the better that the more significant figures we can use. Right? The main takeaway from right now, however, is that these decimal places right here is shared. The last decimal, not that it's the same value. You know, it could be like, let's say this is 5.7, right? The last decimal place, let's say, is the same. It's not that it's the last decimal, it's that it's the last decimal place is shared. So this is the hundredths place. So 10, 1, 10th, hundredths, 10th, hundredths. So we write these both to the same value. So I'll just say that last decimal place is shared. Right? Okay, that's a long-winded explanation, and I'm just trying to produce as much context around this as I can. So yes, standard deviation, right? So that's to make this point right here. Now, okay, degrees of freedom. That's so strange how that's written, right? Degrees of freedom. It's like I am Groot for some reason. That makes sense to me. And degrees of freedom is n minus 1 if you're only deriving like one value from the data set. Does that make sense? So n minus 1, if you just have a collection of the same value and just making an average from it, the number of degrees of freedom that you have in determining the average is n minus 1. Right? So that means if you only have one data point, then 1 minus 1 is 0, and you have no freedom to decide what the average or standard deviation is, right? So, so that's sort of the meaning of that, you know. And then variance is the square of the standard deviation. I have no idea why that's so important here. And then the relative standard deviation is just 100%. This should say percent here. Anyway, 100% times s divided by x. Okay, good. So, and my God, let's find the average and standard deviation of the data set. Okay. So, just to go through this once, and if you haven't seen it, then own up because it's coming back. It's coming back at you. So, so if we have a population of x sub I, right, equal to 821, 783, 834, and 855, then x bar will simply equal 821 plus 783 plus 834 plus 855, all divided by 1, 2, 3, 4, all divided by 4, which is equal to 3293 over 4, which is x bar will equal 823.25, right? And the standard deviation then, and you can see how, you know, this is like the only time I ever want to do this. I'll always use a computer to do this normally, right? Standard deviation is going to be 821 minus 823.25 squared squared plus 783, right? 783 minus 823.25 squared plus 834 minus 823.25 squared plus 855 minus 823.25 squared all over 4 minus 1 in this case, and everything square rooted, right? So the raising to half, that means square rooting the answer, right? So S, in this case, can be 30.2, which we're going to round to 30, right? Because we only have 4 data points. Okay, so that's all we're going to do with that. So, so we do that. Oh yeah, and then the relative standard deviation is you just divide 30 by the answer, 3.7%. This should get a percent, right? And then that's how that works. And then blah, 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 that's how we do that. So now let's go to Excel and do this whole thing in Excel. And so what we would do is we put in the values, 821, 783, 834, and 855. Right? These are the X and Y, right? And then the average, to get the averageness, we go to another cell that's average, right? And then we open a parenthesis, and then we click and drag down on that set, and then close the parenthesis and hit enter, and then that gives us our average, right? And then our standard dev here, this is going to equal the STEV.S. It's not going to be terribly different. It will be different for this small population. Right? And it gives us a ridiculous number of sig figs here. So what I'm going to go is I'm going to decrease the decimal here. Right? And really what we want to do for reporting purposes is we want to do this. Right? This is really what we know about this population, is that the average is 823 and the standard deviation is 30. We really don't know about that 0.25. Yeah, could be, could be not. There may be certain strange circumstances where we can keep those decimals that normally in experimental science we would want. Okie dokie. Cool. So now there's a little unit here on using the properties of a Gaussian distribution to predict the probability of an answer lying within a certain range of this distribution, right? So here's a little head tweak for you to think about this. The probability of making any exact observation is 0, right? So let's say we have a population with an average of 0 and a standard deviation of 1, right? So what's the probability of making an observation of 0.1 or 2.74526? Well, that probability actually turns out to be 0 because you can't assign a probability to a single value. Now, if you give a range of values, then you can assign a probability. Right? So the range of values, for example, between -1 and +1 standard deviations, this z value, this is in standard deviation. And z is in standard deviations and difference from the mean. So like, because here we have x minus mu over sigma, right? So if x is equal to the mean, then u minus mu is 0 and z is 0, right? And then so this is distance from the mean in units of standard deviation. So because you divide by s. So if you go 1 standard deviation below, z is -1. Go 1 standard deviation above, and z is +1. Okay? So that's kind of how we read this in this z space, right? And we can say, for example, what the probability of making an observation between z equals -1 and z equals +1 is, and that is normally 65%. Right? So now here's the Gaussian function, y equals 1 over sigma times √2 pi. Not how pi, it's friggin' everywhere. How's that? Anyways, 1 over sigma times √2 pi times e to the minus x minus mu squared over 2 sigma squared. Right? So this is the negative exponential of the distance from the mean squared. That defines how this falls off, right? And it goes to 0 very quickly. You know, after maybe 4 standard deviations, it's gone. You know, so rarely will we include data from values that are greater than plus z equals 4 or less than z equals -4. Just for your information. Just for your information. So now this is a weird ass statement. Right? And I don't actually think we're going to use it that much. But let me see if I'll go and I'm going to show you a graph of this table that is here. And this table is really, zoom in on this puppy. Here. This puppy here, this is, this table goes from 0 to 4, right? And what it does is it's mapping out the cumulative probability of making an observation between the mean and these values up here. Right? Now let's go back to this table, right? Now this guy starts at 0. So this is really this graph minus 0.5, right? So this is going to go up and sort of max out around 0.5. And this guy comes from a norm dist, norm.dist, right? So let me actually add here. I'm actually going to I'm just going to make this false. So we can look at the difference here. Right? All right. And now let's add a series here. And y value is 2 here, and then so here is the parent distribution from which this comes, So this is the this blue guy is the integral of this orange guy here. Does that make sense? So between minus infinity and 0, you've got half the total area. And between 0 and plus infinity, you've got the remainder of the area, right? Now, infinity here being, actually minus 1. So between minus 4 and 0.5, you basically accounted for all the area in this Gaussian. And then here is the Gaussian itself, right? So, what I was trying to say about this. Let me go back to it. Yeah. So what we're going to do with this is that we're going to take and we're going to make estimates of the number of coin tosses that give a result within a certain range, right? So, so where we're going to start with that is the idea of throwing coin tosses with fewer than 15, right? And fewer than 15 heads is a range, right? So it's from basically 0 to 15. Right? And so what that means is that in this distribution here, we're going to go from 0 to 15. So 0, call this minus 4, or whatever 0 is, minus 50 to the mean, which is 25 minus 10, right? So here that's going to be, and then you know the standard deviation, right? You have to get the value in units of z. So, and then we're going to say, okay, what's the probability of making an observation? 15 and fewer, that's going to be this value here. This value right here, 15 and fewer. And so what we should get is a number close to 1, right? Because that was actually, in this simulation here, they simulated 400 tosses, 50 coins, right? So it's sort of a strange experiment because every quote unquote toss has 50 outcomes, right? And on average, those 50 outcomes should give 25 heads and 25 tails, right? But they never give it, well, they rarely give exactly that amount of heads and tails, right? Well, not rarely, actually, most likely give that. I'm so stupid. Anyways, it's most likely that they give those, right? And then, but then we're asking how often in this toss of 50 coins should we get 15 heads or fewer, right? Given an infinite number of tosses, like how often will this 15 heads or fewer, how often will that crop up, right? And so, let's see. So the way that we're going to do this is, let's switch over to the document camera now. Woo! An interesting phenomenon happening with that computer fan, which is working overtime. And of course, so So what we're doing, oops, wrong one. This is my blue paper here. So what we're talking about here is 50 coins. I'll just like shake them up and slam them on the desk, right? 400 times. And every time, count the heads and tails, right? Then the question here on the table is how many times are fewer than 15 heads observed? So fewer than 15, this is a range, right? And so so what we can do here is first we want to calculate Z. So X bar is equal to 25 and sigma is equal to 3.54. This is the standard deviation for 50 coins. And so Z in this case will be 25 minus 15. Actually, I'm sorry. It's going to be 15 minus 25 over 3.54. It's X bar minus U divided by sigma. Right? Or equivalently, you could say X bar minus U over S, right? Sigma and S are S approximates sigma, just like X bar approximates U. This is actually X test, it's not X bar. X test. And here we could say X bar, right? So Z is equal to X test minus U over sigma, which is approximately equal to X test minus X bar over S. Does that make sense? So here, the Z value that we're going for is 10 over 3.54. And enter 3.54 divide. This is equal to, that's actually minus 2.82. So what we can do is we can ask ourselves, well, what, let's see how to make this make sense. Actually, I didn't go over this in my notes, so I'm like flying blind. Oh, how am I going to finish the table by what is this doing? Okay, so that's going to come out to minus 2.8, right? So for table 4, when the area between the mean and Z is 0.4974, let's look that up. Look at this value. Z is minus 2.8, right? 2.8 here is 0.4974. This is plus Z, right? Ah. So So, so the complement to that area. So basically, what we're saying here is that let me go back to the document. So what they're saying there is that this strange sort of diagram that they have, which is the top half of this cumulative probability distribution, is um, they've taken the area here out to 2.82, right? And they say that this area here is equal to something like 0.497, right? So the remaining area that's out here is equal to, because this maxes out at 0.5, the remaining area is equal to 0.500 minus 0.497 equals 0.0038. And 0.003 times 100 is about 1, right? So you expect in one, about, approximately, on average, to observe one of these 50 coin, of these 400 coin tosses to yield a result with 15 heads or fewer. And that, guys, is where I have to leave it today. And I don't think I need to hide that this is not my favorite way of doing this calculation, nor is it really my favorite calculation. I'm going to go ahead and cover this. And I'll show you an easier way to do it next time using a spreadsheet. Okay? And so so that's it. And are there any questions or anything else that anybody would like to bring up?
Professor, for the exam coming up, what is
Yes.
it going to be?
It's going to cover the chapter we're working on now, chapter 0 through this is chapter 4. So the
Is it
homework
going to be? Sorry, go ahead.
No, so it'll be it's going to be a 50-minute midterm, so it's going to be short, right? I'm just going to have to select a few problems from the homework that you guys are doing, the sampling homework, and I'll just change the numbers and then boom. So maybe I don't know, 5 questions, 6 questions. There might be some really easy like multiple choice stuff we can work through, but then maybe maximum 4 or 5. Does that make sense?
Yeah, that makes sense.
Yeah. Is that? I mean, normally I hate hearing the answer to that question. Alrighty. Okie dokie, guys. Thanks so much for your attention today. And I look forward to seeing you all on Thursday.
Thank you, Dr. Terrell. Have a good one.
Thanks, Evan. Bye-bye.
Bye-bye.